This chart captures a mid-2020s economic shift. The flat line represents small satellite manufacturing costs. The rising line is launch insurance premiums. They cross right here. Insurance quotes eclipsed the physical hardware cost, moving primary financial risk from the clean room into the launch phase. Space economics has shifted from the era of the artisanal, bespoke satellite to the mass production of standardized, commercial off-the-shelf components. This forces a change in how space ventures secure capital. Investors are moving away from underwriting research and development and are instead focusing on execution risk, whether a company can launch at scale and secure a customer before the funding runway ends. Mastering these inverted orbital economics has become the decisive factor in the modern space race, outweighing national prestige or raw launch counts. India has entered a narrow historical window where policy choices made under uncertainty will lock in its space sector's trajectory for the next several decades. The transition from a state-led ISRO model to a private sector authorized by InSpace structurally repeats India's 1990s shift from a state monopoly telecommunications sector to a commercial ecosystem. This intersection defines the current landscape: rapidly falling barriers to entry, technological merging with adjacent commercial sectors, and state institutions originally designed for a narrower legacy mission. Missing this specific liberalization window carries a compounding cost. As seen in previous technology cycles, nations that delay regulatory adaptation in emerging infrastructure face a strategic lag that takes generations to correct. The regulatory choices made today will determine whether India helps write the global rules of orbital commerce or merely adopts the rules written by others. The proven viability and rapid turnaround of reusable orbital-class rockets is the primary engine driving down the cost of access to orbit. This triggers a chain reaction where a single input cost reduction ripples through the entire value chain. The first direct effect is the economic viability of compact, faster-to-build hardware, like this satellite currently in assembly. However, assembling these systems is distinct from achieving component-level manufacturing sovereignty. Relying on foreign supply for specialized radiation-hardened electronics creates a critical bottleneck. When cheaper hardware pairs with cheaper launches, high-density mega-constellations become financially viable at a scale previously impossible. These dense satellite networks unlock services that were previously too expensive to operate, such as persistent Earth observation and global low-latency broadband. This shifts the industry's competitive landscape. Companies can no longer rely on hardware superiority alone. They must differentiate on the quality of the service delivered to the end user. Reusable rockets have rewritten the survival criteria for orbital business models, moving the industry far beyond a mere reduction in per-kilogram costs. These falling hardware costs eventually hit a physical limit: the finite availability of space in specific orbits. Geostationary orbital slots and usable radio frequencies are absolutely finite. This rigid barrier represents the hard physical constraints of our orbital infrastructure. Satellite spectrum allocation is a contested resource, requiring complex coordination with terrestrial telecom networks to avoid signal interference. Policy must distinguish between these genuinely scarce, internationally fixed resources and adjustable domestic constraints, like foreign investment ceilings and licensing delays. The access right stack, successfully securing spectrum, slots, and licenses, has surpassed engineering risk as the definitive hurdle for venture viability. While launch capacity can be scaled, orbital real estate cannot. This makes regulatory allocation the true strategic choke point of the space economy. We are currently seeing the complete dissolution of the boundary between orbital infrastructure and terrestrial digital networks. This merging is occurring across 4 primary technological zones: 5G and 6G satellite communications, space-based Internet of Things, in-orbit servicing, and quantum communications. Direct-to-device messaging now links standard consumer smartphones directly to low Earth orbit, removing the need for the bulky, dedicated terminals used in the past. Future 6G network specifications are being designed to treat this satellite connectivity as a native core component, rather than a separate overlay. Simultaneously, space-based IoT networks are bypassing terrestrial dead zones to provide persistent monitoring for remote agriculture and maritime logistics. Beyond data, satellites are now distributing the next generation of cryptographic security through global quantum communications networks. In-orbit servicing provides the physical maintenance layer for this expanding digital architecture, refueling and repairing satellites to extend their operational lives. In this environment, treating space policy and telecom policy as separate disciplines creates dangerous regulatory blind spots. Agile commercial enterprises are currently forced to navigate regulatory structures originally built for the state-led ISRO era. To operate legally, a single commercial satellite startup must secure distinct, often uncoordinated approvals from the Department of Telecommunications, InSpace, the Ministry of Electronics and IT, and TRI. These intersections create bureaucratic friction, subjecting startups to contradictory compliance formats and deeply delayed approval timelines. This distributed architecture leaves critical gaps. For example, current localization laws are unclear on who governs high-resolution Earth observation imagery of Indian territory when it is captured by a foreign operator. Terrestrial ground stations also face significant, underweighted cybersecurity vulnerabilities that remain largely unaddressed by the current multi-agency framework. For Indian startups, this friction contributes to a persistent financing hurdle, the gap between technical success and commercial viability. Aerospace hardware startups frequently exhaust their capital runways in the dead zone between successfully validating their technology and securing their first commercial contract. Bridging this gap requires a pivot in government policy, moving from merely granting early R&D capital to acting as a reliable early-stage anchor customer. Converging our digital networks with orbital hardware introduces inescapable strategic vulnerabilities. Most orbital assets are inherently dual-use in nature. A standard commercial Earth observation satellite designed for crop monitoring possesses the exact imaging resolution required for military reconnaissance. While modern electronic warfare relies on signal jamming and spoofing, traditional kinetic deterrence rests on the threat of physical destruction, as seen in the scale of the Mission Shakti missile. Because orbital assets are extremely fragile and expensive to replace, deterrence in the space domain relies on mutual restraint rather than active physical defense. Modern attacks rarely target the satellite directly. It is often simpler and more deniable to execute a cyber attack against the terrestrial ground stations that control the spacecraft. Any agenda for commercial liberalization must proactively navigate these strict dual-use security realities. When a space asset fails, the disruption instantly cripples banking settlements, telecom backhaul networks, and ground-based disaster response systems. This exposes a very dangerous operational lag, the time it takes to determine which specific government agency owns the response when a technical anomaly occurs. Distinguishing a hardware fault from solar weather or a deliberate spoofing attack requires coordination that current institutions are not yet rehearsed to provide. To manage this, we apply the attribution ladder, ranking incidents from environmental interference at the bottom to deliberate state action at the top. This framework uses pre-agreed authority matrices to immediately assign agency leadership for each threat level. True resilience is achieved by institutional design and civil-military coordination, rather than simply hardening the hardware. Resolving these challenges requires a regulatory convergence stack. By streamlining the competing mandates of DOT, InSpace, METI, and TRI into a single cohesive framework, India can eliminate the bureaucratic friction currently stalling commercial capital. Space dominance in the coming decades will belong to the nations that engineer the most predictable institutional frameworks today. These choices will determine if India operates as a global rule shaper or a rule taker.